Hello, math fans. I'm Andy Lovelace. I'm an instructor at the University of Washington. I've started to make a collection of videos of interesting problems I've encountered and how they relate to things that I love in my life. I hope this gives you a little insight into some mathematics, maybe to some problems, but mostly it gives me a chance to highlight some of the things I love, some of the people and places I love, and to share a little bit of math along the way. So years ago, I teach many calculus courses. In 2010, 2011, and 2012, I taught this honors calculus series where I had these 60 incredible students and I would teach them for the entire year. And we did normal calculus stuff, but we'd also do some projects. And I tried to come up with interesting projects that would apply to many of them. But the truth is, they're the only ones that ever saw those projects. I never got to share them more widely. So one of the projects was, how far is it to the horizon? Now, this is not an original question at all. It gives students a chance to start thinking about tangent lines. And I'm sure many people have done this. If you want a copy of my project and what I wrote, I'll show you it in just a second. And you're welcome to use it in your own classes. But as I go through old projects I did that I never got to share, I start to think about things over the last many years that have become important to me. And Manzanita, Oregon is one of those places. Here's a picture looking down from Neahkahnie Mountain just above it. My family and I have gone there for 14 years, about every summer. It's just a lovely place, small town. We all love the beach. It's a week where we're all nice to each other. It's located here. I live in the Seattle area, but it's located on the Oregon coast. And it's just lovely. I love Manzanita. I'd love to just move there and live there all the time. We love the candy shop, the ice cream place, the bookstore, Unfurl, all the places there, the shops. We go to the park across the way. It's absolutely lovely. My son, who's about to go off to college, and I can't think about it, or I might start tearing up here, but we hiked to the top of Neahkahnie Mountain. He is in incredible shape. He's a cross-country runner, and I am completely out of shape, so I barely survived. But we made it to the top of the mountain, and this is us looking out. Here's a view of where we were. We were at the top of this peak, looking from the city. These clouds are incredible. It's on the other side looking out. And so I just was thinking about this problem that I had students do. That was the distance to the horizon. It was basically this question. We're on Earth, very big. We're making things idealized. The Earth is not a perfect sphere, but let's pretend this is the Earth from the side. And up here we have Neahkahnie Mountain. And we have the radius of the Earth, this little thing I'll call R. And we draw a line. We draw a line that goes out to the horizon, right there. Out here. So the good question might be, how far is that? How far is that from us? This line of sight question, or distance to the horizon, certainly it's a question that's been asked many times. How would someone go about solving that? So ultimately, and I'll talk about my project in just a second, and I hope that this gives a little insight to, for my son. I don't know that he'll appreciate this video. He may not appreciate me showing a picture of him there. But, all these years as I've been doing projects with students, and I hope at some point you can appreciate some of these little things. You're already much smarter than I am, and I love you so much. Anyways, here we go. So we have this distance is R, and let's call the height of the mountain H. This is going to be R plus H. And when I did the class, I had students prove it in all sorts of ways. The real reason we do this in calculus is an opportunity to talk about tangents before we know derivatives. And so this is our first couple weeks of our calculus course. We do problems like this, some more challenging ones where the tangent has to hit. But this is a tangent line. Tangent line means it just touches. If you have some curve, this is what we call a secant line that hits in two places. But if you take this point and move it a little closer like there, then it's a secant line still. But the closer this point gets to that point, it'll look more and more like what we call a tangent line. And that is where calculus starts. That's where the definition of the derivative starts. Okay, so we have this point where it's tangent. And the main observation about a circle is if you have a point, it doesn't really matter where it is, it's tangent. And then you draw a line from the center, which is called a radial line. Those two lines are perpendicular. And I hadn't planned to prove that in this discussion. You can definitely see it when you go straight out towards this side, that those would be perpendicular, and it shouldn't matter by symmetry where it is. So whether I have convinced you or not, this is a right triangle. This triangle that I just formed is a right triangle. So this is probably the shortest proof. I had the students do it a couple different ways. So this thing is R, and this other side is R plus H. I know it's tough because we're working with these unknowns, and then the thing we'd like to find is this distance, how far it is from there to there. That's what we're trying to find, this distance. So it's the Pythagorean theorem yet again. If you're watching some other videos, it seems to pop up from time to time anytime you're dealing with distances. What do I mean by the Pythagorean theorem? It says a squared plus b squared equals c squared. Maybe a proof of that might be interesting in one of my future videos. Let me know if that would interest you in the comments. So we have r squared plus d squared, those are the two sides, is equal to r plus h squared. And so we're trying to find d, so you get d squared is r plus h squared minus r squared, and we've done it. The distance to the horizon is the square root of r plus h squared minus r squared. And you can't simplify that. That's called the freshman's dream. When you cancel the squares and the square roots, that doesn't work. I mean, you can simplify. I shouldn't say that. You can expand underneath, but you can't cancel the square root. This is plus 2h plus h squared minus r squared. I don't know if I've gotten a chance to mention this in this video. Again, I'm mostly just going to, after we finish this piece, I'm going to survey a few things, and then I'm going to answer the question, which I've never answered before. It's going to be new on this video. How far is it to the horizon from the top of the Neahkahnie Mountain? But anyways, just because I don't think I've ever done this on a video, we're going to multiply this out. If you multiply this out, it looks a little bit like a monkey's face. There's the eyebrows, there's the nose, there's the mouth. One of my wife's teachers in high school always would say, you need to monkey face it out. A lot of students call it foiling. I was just observing a TA who was teaching, and the student said, you need to monkey face it out. The TA was like, what are you talking about? And I just sat in the back laughing, knowing that that student had listened to me. I unsuccessfully, look at this, I made a mistake. I didn't monkey face it out. The middle one is RH, and RH, that's 2RH. And these R squareds cancel. I don't know what's simpler to compute. Sometimes students think that there's a magic rule. You'd like to make it user-friendly, but one formula is that. The other formula is 2RH plus h squared, and you could factor out an h. So we could play this game all day and then debate about what we think looks prettier. But there's our formula for the distance to the horizon. R would be the radius of the Earth. H would be the height of the mountain. So before I talk about the write-up, just a little bit of history, just because to me, this is more important than the math. I think we spend too much time being stuffy and talking about the math. But I looked this up. We've gone to the Historical Museum in Manzanita before. I didn't hear this there, but the name Neahkahnie means place of the gods. And when we're up there, it certainly feels like that. There's some interesting history. For a while, people thought that there was a buried treasure chest up there. Anyways, I just thought it was interesting. There's also a history of some shipwrecks and some of the names of some of the streets have been named after some of the things that they found. Anyways, so here's the actual story. This was the write-up I did. And this was a long time ago. I was a little stuffier back then myself. Look at how dense this is. I would never write it like this again. So many different questions I asked them. And then I was really picky about write in complete sentences. It was an honors class. They were willing to let me say that. And then here's this artifact. You may not know this, but that's paper. And I had to scan it in. And it was not easy to scan paper. I had to use a scanning device. It wasn't like it is now. But I wrote this thing up. We defined the horizon to be the farthest point on the surface. Blah, blah, blah. And then I did it using kind of the calculus approach by talking about slopes and that these two lines are negative reciprocal slopes of each other. Maybe you've heard that before or not. I set up a couple of equations that led to, and this is the long way to do it, that led to me finding the point. This is the point of tangency, the point where it touches. So I learned a little more that way. And then I used the distance formula to find the distance between them. And then I said, oh, by the way, there's a shorter solution. But I liked in these ones to do things a few different ways. It's nice to see that you get the same thing. And then I made students figure out the distance if they're just standing on the surface of the earth. And we're assuming, there's nothing in the way, the earth. This is just an idealized story. I also had them find this so-called arc length, which is the edge along the surface of the earth, just to compare. That's the arc length from your feet to that point. So I thought it was kind of interesting to compute both, and I talked about that formula. Just a chance for us to mix in some other things. And then I had them say, okay, what if you're 6 feet tall? And we plugged it in. So this is the radius of the earth. And again, that formula was the square root. Let's look it up again. The square root of 2RH plus h squared. Let's use that one. 2RH plus h squared. So for r, I put in the radius of the earth. You could play this game yourself, rounded to one digit. And then I converted everything to miles. So then I replaced h with however many miles it was. So 6 feet is 1 over 880 miles. Don't ask me why a mile is 5,280 feet. I'd have to look that up. So I plugged it into both these formulas. The distance on a straight line was this. I also plugged into this formula and I got this. And they're going to be pretty darn close because of the radius of the earth being so large. And then I did the distance from the top of the Space Needle. That's what I required them to do because we were Seattle people. And from the top of the Space Needle, it's about 28 miles that you can see. So if you're just standing on the surface of Earth and there's nothing obstructed, so if you're standing on the beach, you can see about 3 miles. If you're standing in the Space Needle and you look out to the water, you can see about 28 miles. And then I had them do different questions with limits. That was fun. But the question I wanted to ask for my son was, okay, Neahkahnie Mountain's about 1,600 feet high. So let's plug this in place of h and see how far it is to the horizon. And that's higher than the Space Needle. So I did this. I pulled up this computation. I plugged in. There's my r. There's my h. I was a little lazy and didn't get it as a decimal. I'm plugging in an online calculator, and we're getting about 49 miles, almost 50 miles. So it's about 49 miles to the horizon. I did the other calculation that's how far is it along the Earth, but that was also about 49 miles. And then I just found a random website. There's lots of these. And you can put in anything you want. And you can see, it's 49 miles. So it's just nice to see that you get the same thing that I'm saying. And then I did some other problems relating to limits and formulas. But mostly I just thought it was interesting. I talked about what happens as the numbers get bigger. How do things deviate a little more? That was kind of fun. So anyways, I've never answered this question before. I just was thinking about it. That out there is about 49 miles away. So the next time, Danny, we're up there, we can say, well, that's about not quite 50 miles out there. Now, there's probably issues with how far your eyes can perceive. I'm sure that's a separate question. And just while I'm on this, my love to Manzanita. We've spent many years digging out there. We all love digging. My wife and I love it out there. Love you, family. Thank you so much for our time there. Thank you, Manzanita, for being there. Hopefully one day I can retire there. If I do enough weird videos, maybe they'll fire me and then I can go move and run the hot dog stand in Manzanita. That would be lovely. So watch this video, tell them to fire me, and I can move to Manzanita. All right. Love you, family. Love you, Manzanita. And the distance from the top of Neahkahnie Mountain to the horizon is about 49 feet.